So how these compounds can be synthesized? Let's say we have a double bond present at this position, then we add bromine, so these shall be added, bromine above and behind the plane, totally opposite to each other. So these are the two isomers. You see, we have in fact this tertiary butyl group above the plane. Here tertiary butyl is behind the plane. This is the only difference between the two isomers. They are also epimers in fact. Let's see if I draw the confirmation of the structure number 3. This is the confirmation I have presented. You see two bromines are present at this position, and this is the tertiary butyl group. Keeping in mind this tertiary butyl is called a locking group. This is a locking group, just like you have seen this system. Trans ring junction are also locked due to conformation. Trans ring junction is also locked. It cannot flip over to the other chair, whereas cis ring junction can flip over. All right. So here, this group, which is a tertiary butyl group, is a locking group. If let's say I have presented this here, this is above the plane, equatorial. If we cannot place this axial, if we place this axial, it shall be sterically too much crowded, because 3 methyl, each methyl have 3 hydrogen, shall couple with a proton hydrogen present here and this bromine. It shall have a too much steric hindrance. You have already studied in previous semester in stereochemistry. You can't have a tertiary butyl at axial position. It have a 0% conformer. 0%. So that's why whenever you have a tertiary butyl group, it always go to equatorial position. So sterically crowded entities we place first, and then relatively other are placed. So I have placed this group here above the plane, but equatorial. You see, leaving one carbon, which is this one. We have a bromine behind the plane, which is this. It is axial. This bromine is above the plane, so this is also axial, but both bromine are opposites. Now there are various possibilities. This bromine can leave and a hydrogen from here, because the hydrogen is axially downward here. It can undergo elimination. Similarly, this bromine, if leaving from here, hydrogen is not axial. It cannot. We cannot undergo one bromine leaving and we get a double bond here. We cannot generate, because if this bromine is axial, if this is leaving, the hydrogen is equatorial. So they are not undergoing to generate a double bond at this position, or vice versa. If this bromine is leaving a hydrogen from this lock, no, not at all. This bromine can leave, and this hydrogen at axial can leave without electron pair, generating a double bond here. Another possibility is here, this bromine leaves from here and a hydrogen present here leaves without electron pair. So two isomers are possible, one double bond here and a double bond there. So they are not same compound. They are two different isomers in fact. Now look at here. If this group is behind the plane, we cannot draw it again axial. So that's why I have presented this equatorial position again. And the other two, this bromine is behind the plane, this bromine is above the plane. Now these bromines are not at axial position. They shall not undergo elimination, because if this cyclohexane flips, then this bromine shall go to axial position. But again, this tertiary butyl group shall also go axial. So we shall have 0% contribution. That's why it is not let this group has lost the conformation. Now it is this chair conformation is not going to flip to the other chair. That's why this substrate shall not undergo, this isomer number 4 shall not undergo elimination, but number 3 shall undergo elimination. These are just a few applications I have presented here in E2 elimination mechanisms. So anyhow, this is all about this course. So we have discussed the addition, substitution, and elimination reaction in this course. So next semester there is another course, reaction mechanism, in which pericyclic reaction, molecular rearrangement, redox reactions, and free radical mechanism shall be discussed. So anyhow,